are gathered here to talk about how to build a pair of South African Sign Language gloves, which, as you can see, I have the signs over there. I thought we could keep this super interactive, so let's start off with a simple true or false. If you agree with the statement, clap after I say true. If you don't agree with the statement, clap after I say false. Obviously, don't clap for both, or you'll just cancel yourself out. But so for the statement, South African Sign Language could be our 12th official language. Is it true? Clap if you agree. Or is it false? Clap if you agree. Not even a single clap. So yeah, thanks so much for clapping for true. But if you haven't been living under a rock, you will have seen every single headline lately, which is all about how South African Sign Language is on its way to become our 12th official language, which is really, really exciting. Basically, President Cyril just needs to sign it in, but it's already gone through the relevant procedures. And honestly, I couldn't have asked for a better headline, as I'm here today to talk about South African Sign Language. So it's almost like I planted this in the news myself, which I didn't. But just a full disclaimer before we begin, the gloves aren't here, so if you are here to see them, I'm so sorry. Feel free to walk out if that disappoints you. But I do have a lot of good code snippets, some good montages of me building them, and some videos of them in action. They were just too big to travel with, and they don't travel well like me. The aim of today's session is you're going to be leaving here with the knowledge of how to build these on your own. I'll be sending out a recipe card so that you can go forth and build your own gloves should you wish. And throughout the session, we'll be keeping it super interactive for different kinds of Stitch giveaways. So I like to call it participation swag, because if you just raise your hand, you'll get something, which is my favorite kind of medal. Cool. A little bit about myself. My name is Thalia, and I am a full stack engineer at Stitch, along with these two guys on the front. I love South African Sign Language, and I also love building things. I also love building diverse teams. So if any of those interest you, please feel free to find me after this talk. I've actually been coming to DevConf since 2019 and have always had the best time here. So really, really excited to be here with you today. What makes me qualified to talk about this? Probably not much, but I did study mechatronics engineering at UCT way back when. I used to build a lot of things in my spare time, and these gloves were actually one of them. And I spent about 6 to 8 months on them. So it's going to be a bit hard to condense it into 40 minutes, but we'll try our best. If you feel that it's too shallow, I'm very happy to go into more detail with you afterwards. I'm not really an expert at South African Sign Language. I did teach myself it for the purpose of this glove, and this is just purely for my own interest. Cool. In terms of the structure of the talk, it'll be split into 4 sections. We'll start off with going into a little disclaimer on what SASL is, the different components of it. I'll then go into the hardware side, which is the components you need for the gloves, as well as how to assemble them. We'll go through some classification exercises, and then we can end off with where to next. In terms of South African Sign Language, so it's a visual spatial language which primarily uses the hands as a form of communication. It does actually have influences of Irish Sign Language, as Irish nuns used to teach sign language way back in the 1800s. It's slightly different from American Sign Language, and there's also regional variations within South African Sign Language. So people signing in Cape Town might have different interpretations of the same signs in Johannesburg. And this does make it quite hard to learn, as there's no single comprehensive database on it. But there have been really great efforts by an initiative called FingerTalk. In terms of the ethics behind these gloves, I always think it's really important to go into that as well. So a lot of the research I did when I built these way back in 2018 were like very heroic, trying to give a voice to the voiceless. And that's not really something I believe in. Like, I think, these gloves are cool and all, but there's still a lot of work that needs to be done to be truly assistive. And yeah, so I just want to lead with that preface to make sure that no one thinks like someone whose like primary language is South African Sign Language is going to wear these immediately. There's still quite a bit of work to be done. The 5 parameters of South African Sign Language are the building blocks. So we have hand shape, orientation, location, movement, and non-manual features. For hand shape, just the shape of your hand, nothing fancy. You could have static poses, dynamic poses, and then continuous gestures, which would be like sentences. For orientation, that's really just the way your palm is facing. So it can be used to denote ownership. So like very similar gestures will have different orientations to show the difference between yours and mine. In terms of location, so I thought this one was quite interesting, but you can practically sign anywhere on your body, with the most common area being between like your torso to your below your head, and that is known as the bounding box. In terms of movement, we have hand and arm movements. What's quite cool is the rate of signing also infers different meaning. So if you're signing slowly, that will be something completely different to if you're signing fast. And then lastly, the non-manual features are anything which don't involve your hands. So this could include head shaking, emotions, spatial pronouns, anything like that. And the ones that we'll be focusing on today are hand shape, orientation, and movement, with future work needed for location and non-manual features. I'm sure all of you know hands, as we all have 2, or well, I don't assume. But does anyone want to guess how many bones there are in your hands? No Googling, please. Any guesses? Any guesses? Pardon? 50. Oh, you get a prize for that. You can come collect it afterwards. But the correct answer is actually 27, so half of that. But yeah, so there are 27 bones in each hand. And the main movements within your hand are flexion. So that's like any kind of bend of your hand, so moving the tips of your fingers towards your palms. And then abduction, which is just the opening and closing of your fingers, similar to those horrid machines at gym, which, the leg abduction ones. And then to measure like any kind of sign language, we still need to get orientation into the picture. So the things we'll be measuring today are flexion, abduction, and orientation. Cool. How will we be doing that, though, is the real question. So when I was doing this back in 2018, I found that there were like many ways to measure finger flexion, but not all of the ways should be used to measure finger flexion, if we're being completely honest. The 2 main ones that I looked at were optical flex sensors and then resistive flex sensors. So optical flex sensors essentially it's a tube. At one end of the tube, you have a light source. At the other end of the tube, you have a light-dependent resistor. And then as the tube bends, different amounts of light get transmitted, and that changes the amount of light that gets emitted, and you can use that to determine how much flexion has occurred. What's great about optical flex sensors? A lot cheaper than their resistive counterparts. What's not so great, though, is that they are very affected by ambient lighting sources. So, you might get different results on a very sunny day like today compared to a rainy day. And I just didn't have time to deal with that complexity. So I opted to use flex sensors which were resistive. The ones I specifically used were the ones at the bottom. They were developed by SpectraSymbol in the late 1980s. Apparently they were used in the Nintendo Power Glove. The sensors at the top, if anyone here is from FlexPoint, please don't hate me, but they were like the worst sensors I've ever used. They suffered from a lot of torsion. They just weren't stable. I just did not have a good time using them. To wire your sensors up, you connect them in voltage divider configuration, and then you just measure the output voltage once you blend your fingers. As you bend your fingers, resistance increases, so naturally your voltage will change. I use the 2.2-inch flex sensors on my thumb and pinky fingers, and then the 4.5-inch ones on the middle 3 fingers. What was quite cool, though, is when I built these, I tried to make sure that they could be calibrated to account for different users. So on startup, there was like a short calibration cycle where users could bend their fingers like between their minimum and maximum, and in that way we could calibrate the circuit to ensure that we knew what their specific max and min angles were. This is some of my Arduino code, which I'll be sharing with you guys afterwards, but essentially it's just mapping that output voltage to an angle by sampling the ADC. Moving onwards, to measure abduction, I opted to use a capacitive sensor. And what's quite cool about a capacitive sensor is it's very easy and very cheap to build, which are two of my favorite things. So with capacitive sensors, how it essentially works is Arduino has a library aptly titled capacitive sensors, and then you need 2 pins, so one for sending and one for receiving. And then on the receive pin, you end up connecting some capacitive thread. I just used 2mm capacitive thread for this, and then you essentially use your Arduino to measure the time taken for the capacitor to charge, and based on that time constant, you can then detect how far things are away from each other. So instead of just getting a binary high-low, you also get like a range of values if the fingers are closer together versus further apart. Cool. And then the last one, which was motion, arguably the most difficult one. I used a good old inertial measurement unit to measure motion. The specific one that I used was the Adafruit BN0055, which was a 9 degree of freedom IMU. I don't know if I'd recommend it. I think it was great. It was just a bit expensive, and like I was on a student budget at the time. But even now, I probably wouldn't buy it again. But within it, it is super powerful. It does have a gyroscope, an accelerometer, and a magnetometer. And it can also measure temperature if that's what you want to do with it. And what was quite cool about the IMU is you could essentially determine orientation using the quaternions. So that lovely snippet on the right is some quaternion maths where you just multiply the quaternion by its conjugate in order to get rotation. And how that looks like in the code is this, which looks a bit scary, but it's actually really not. And if you look at the bottom right, what that outputs is a direction of 100 if your hand is pointing upwards, and then a direction of 0 if your hand is pointing downwards. If your hand's like flat, that would obviously be 50. But using this, I was actually able to get really accurate readings and able to accurately get the orientation of the hand. Cool, this was the final design per hand. So we had the 5 flex sensors, the 5 capacitive sensors, the IMU, user Arduino Pro Mini 3.3 volt, also used a 3.7 volt LiPo battery. I used a Bluetooth module, the SparkFun Bluetooth made silver. Also, it was okay, it wasn't bad, it was just a bit hard to integrate with. And I'll show you what I saw it was shortly. In terms of assembly, so now that I had all of my components, I needed to do something with them. And I'd really just breadboarded for ages, like for weeks and months, mainly because a lot of my components were constantly stuck at customs. So especially the flex sensors, I think I argued with customs for many, many moons. But on the far left, you'll see the breadboarding I did. And then on the middle, actually even before the middle, there was a stage where I opted to just like scrap the gloves, and I was like, who needs gloves? Let's build an exoskeleton. And then at that point, I just used cable ties to put the flex sensors onto each finger, which you can imagine takes really long because it needs to be fitted like very flush against each finger. And then when you had to take them off, it was just like pure agony because you had to cut off each one individually. So not scalable. I wouldn't recommend that. The middle one was actually probably the second or the third glove. There was like a winter ski glove before that, but it was so hot because I was doing this in summer, and I would like almost faint when I put that thing on. I used proto board in the middle, which was lovely and always easy to use. On the far right, that's a PCB I designed using Altium, and I got tracks to manufacture it. In true PCB design, it did take quite a while to get manufactured, so I actually only got it once the project was complete. So now it's actually just a lovely keyring on my book bag. And here's like a very fun assembly montage of myself building the gloves. Like when I did this, I didn't really think I'd show this to anyone. It's just a time lapse. Like you can just see like what a process it was. Like imagine me doing this for like many months. I think I take like a snack break there, come back. There I am soldering. Actually burnt that table really badly. Which was funny because I was trying to sell that place I was staying at the time, and the real estate agent kept coming in and being like, what's going on here? Like, why are there burn marks all over your table? And I was just like, yeah, I just really love some candles, hey? Cool. So this is actually the final glove, which is called Sloth, because it's my favorite animal, but also because it stands for sign language on the hands. You'll see it's pretty snazzy. I think it's aged pretty well. I don't know how well you can see, but there's like these little like rivulets or like trenches, and that's where I would feed in the flex sensors into. And then you'll see all the silver stuff in the nooks and crannies of the finger. That's the capacitive thread we use to measure abduction. I just ended up putting the IMU flush on my hand because any housing just wasn't going to work for it, like it was distorting the measurements. For the wrist strap, I 3D printed that and designed that in Fusion 360. Bear in mind, that's just proto board in there, which is why it was so big. I initially designed it to look like a Rolex, but it didn't really turn out that way. Because that flippin' Bluetooth module, you can see it hanging out there on the bottom of my wrist. But like a Rolex, it's priceless to me at least, and I think kind of got the job done. In terms of the manufacturing of the glove, so I got my favorite seamstress, who's also my mother, to sew the gloves. And you're like, oh, Thalia's mom's so lovely. And she is, she really, really is. But she's also a very busy woman because she's like a dentist, a chef, a yoga instructor, all in one. And looking back, probably shouldn't have asked her to build the gloves. So we live in a rural village up in northern KZN, and so she was building these gloves up there and sewing them and stuff. And then she sent them to me in Cape Town. And I put these gloves on, and I kid you not, they did not go over the tips of my fingers. Like my absolute sausage fingers could not fit into these gloves. And if you guys know my mom, which you probably wouldn't because that's weird, her fingers are like half the size of mine. So then there was a lot of tears, mainly mine, but also a lot of tense words, also mine. And we finally iterated and we got this glove that you see here, and it fit on my hands, didn't fit on her hands, but at least I was able to wear it and do things with it. Cool. So now that we have the gloves, you're probably like, wow, I can go for an early tea break, get that like 5th cup of coffee of the day. But actually, this was where the fun really started. I thought building it would be the hardest part, but it was actually classifying. And even before classification, there were a lot of steps which needed to happen. So we had pre-processing, we had sensor fusion, we were talking about Kalman filters, and then only could we classify the data. So this was quite a journey, but one that I really enjoyed thoroughly. So the first thing I noticed with that good old IMU was when I put a flat on a surface, that thing just drifted into space. Like, the amount of drift on the IMU was atrocious. So then I researched certain concepts, and the one I found which applied to my use case was sensor fusion, which is basically using your stronger signals to overcompensate for your weaker signals. And that's quite beautiful when you think about it, because it's like using your strengths to overcompensate for your weaknesses. And with sensor fusion, a core concept and why it's particularly useful is not all states are directly measurable. So for example, with acceleration, we have to integrate it twice to get position, but every time you integrate it, your drift error increases. So using something like an extended Kalman filter helps remove that noise and just helps you have a much easier time when classifying your signs. The two models I looked at were complementary filters and also extended Kalman filters. Complementary filters, very chill to implement, just a combination of high and low pass filters. They don't do so well with 9 degrees of freedom, which is what we had here. So I opted to use my favorite filter, the extended Kalman filter. And how that really works is it just helps model nonlinear functions. It's exactly the same as your normal Kalman filter, except it's for nonlinear as well. And the first thing that you do with the Kalman filter is you linearize your system. So if any of you did maths at university, I'm sure you all fondly remember the Taylor series. So that's kind of how I linearized my system and made my nonlinear function into a linear one. Once you've done that, you can then feed it into your system, as we have here, and then you can basically just run predict and update steps in order to compute and predict what the next step would be. I love these funny colors, they're so lovely. But cool, how you can kind of think of it though is like, if you are, let's say, here right now, and you were like here before, because we've linearized the path between those 2 points, we can safely predict that I would be here next. But let's say for some reason I'm like slightly forward or slightly back, we can then update our model with the difference between those states. And you just iterate through that a few times until you have your desired values. So when I fed my data from my accelerometer into the Kalman filter, these were the results I obtained. That light purple line, not sure what color will be on the screen, but that light purple line is like the noisy accelerometer data, and then that black line in the center is actually the value of the true signal. So using the extended Kalman filter, I was basically able to remove almost all of my noise. And what's pretty powerful about that is that it makes classification that much easier, because you're like preloading a lot of the work into pre-processing. And the one thing that you do run the risk of though is over-smoothing, because like imagine that was just a straight line and I called it a day. I probably wouldn't get great classification results then. So that's the extended Kalman filter, really always remains my favorite filter. If you want to talk about the maths behind it, feel free to hit me up. The next thing I needed to do, now that I didn't have noisy data in my accelerometer, I needed to look into feature engineering techniques. And the reason why I needed to do this was with 2 gloves, you have double the number of inputs, so about 28 in total. And you can imagine the dimensionality of that just becomes unthinkable, and you just don't know what to do with all of those inputs. So the 2 techniques I looked at there were feature extraction and feature selection. So on the left, we have feature extraction, which is really where you transform your subspace into a new data set. So you'll have 5 inputs going in, you transform them, and then you're left with 3 inputs. And those aren't the same inputs as the ones before, so you could actually get more interpretability and just get more explained variance in your data set. On the right, we have feature selection, much, much simpler. You just basically lost like a certain number of features. But you know that you do have to take care to make sure you aren't losing any important data. I opted to go with feature extraction just because I was really just looking at this data and trying to make sense of it. And I wanted to try just reduce the dimension in a way which was smart and well thought out. In this figure, this is a process I used. I employed a technique called principal component analysis, or PCA. And basically what that does is it takes your data and it finds the largest variance within it. The first thing you do once you have your data, you center it. Bear in mind, we'd have like as many degrees of dimensions, so it does get quite hard to center it. You then determine your covariance matrix. You break that down using eigendecomposition into its eigenvalues and eigenvectors. You then choose the eigenvectors which have the most variance, because they essentially contain the most data about your data set, or at least the most independent data within your data set. And then you project that and you just kind of go forth and conquer the world. How that looked when I applied it to my data was I found that the first principal component contained about 22.91% of the explained variance. So that was really interesting. Love that. Because just one component now suddenly had almost a quarter of the required data that I needed. And then if we go to the principal component 7th, the sum of the explained variances were almost close to 90%. So just by going from 11 inputs to 7 inputs, I was still able to capture 90% of the variance within the data set, which is pretty powerful. And when I ran classification on it, like even just with those 7 transform components, I was able to achieve the same classification accuracy as I was with like 11 inputs. Cool. So moving on to our last portion, which is classification, and really the moneymaker, if I say so myself. Now that we have the gloves, we've filtered out noise, and we've also found that we can drop some features, the last thing left to do is really just to classify some signs. And the 2 questions I asked myself when doing classification were, what kind of model would be most suited to both dynamic and static gestures? And secondly, would I need to retrain this model every time there's a new user? And I think, especially the second point, it's really important to try and ensure that your system is robust to new users. Otherwise, you run the risk of building something which you have to train extensively and then like test on that, and it's just not scalable or feasible to be rolled out. So for the first question, I wanted something which worked like a brain, and obviously neural networks exist, and I'm very grateful that they do exist, because they're just very intuitive. And because for me, real-time classification was really important, I loved specifically convolutional neural networks because I was able to save the weights and like the configuration and then perform the real-time classification. When I was preparing the data, I created 2 different data sets, so a control data set and then a variable data set. I kindly got some of the, I asked some of the kind members of the dev community in Cape Town to help me generate some data, because that's like a whole project in itself. And together we came up with that control data set and the variable one, with the variable one showing us the effects of signing over time. So like you could get like fatigued over time and like stop flexing your fingers fully, or just a new user would have very different patterns. And then I use good old Python and TensorFlow in order to configure and build out my model. And the final configuration I landed on was this model. So on the left, on the input layer, we have 11 inputs. That gets fed into our hidden layer, which is a fully connected layer. And that's where the magic happens and all the decision-making occurs. And I opted to use 12 neurons there. I varied that between 1 to 30. But I found that after 5, classification accuracy was as high as it could be. But then I picked 12, so as not to get caught in that turning point. You then feed that into your output layer. So for this model, this is purely for the static gestures, so your alphanumeric signs. And here I just chose to do the alphabet. And I know you're going to be like, oh, there's 26 letters, I know. But I think J and Y both require dynamic signs. So for the static model design, I just did the 24 purely static ones, and then I incorporated the dynamic ones into my dynamic model. I then looked at a dropout rate of 0.1, which essentially means that 1 in 10 neurons get dropped. And this is also to prevent overfitting from occurring. And I was worried about overfitting occurring just because I didn't have a lot of data. And overfitting is when, your model is trained on a small data set, so it's not robust to unforeseen circumstances. So by implementing a dropout rate, you're essentially making your model more robust because you're removing a neuron every time, so 1 in 10 would get removed, and that would just help the other neurons make decisions for that neuron. Cool. In terms of the classification accuracy, all these, I guess, to be guessed, were the classification accuracies I got. On the top left, that was for existing users. Does anyone want to guess what that is? And you can win some merch. Anyone? Pardon? What was that? 40%. Oh my goodness. I don't know if I'd be giving a talk if it was 40%. Yourself in the front? Pardon? I thought you said 37. I was like, wow, we're just progressively getting worse. But 97, okay, no, you guys can both get participation swag. But the classification accuracy I was able to achieve for existing users, so those that were in the initial training set, was 99.91. And this is honestly way better. I also expected to get 40%. But what this essentially meant was I never really got any false positives. And specifically for the static gestures, I could almost always be certain that whatever you were signing was what was recognized. Anyone want to take a gamble for existing users? Naturally would expect this to drop. Anyone? Levi? 70. I feel like 70 is still really good though, so I think that's actually not a bad guess. So it did drop slightly. So these were new users which we weren't trained on at all, and they had very different hand sizes, very different flows and methods of signing. But because we had tried to calibrate with them and do all of that as startup, we were still able to achieve a really, really solid classification accuracy. And just in terms of what that means realistically is, here's a video. So only for the static gestures. Quite zoomed out though. But you'll see I just picked 5 of my favorite letters. There's that little printed piece of paper on my wall. And then I'll start signing them. And I used a text-to-speech converter to say it out loud. So let's press play.
A, B, B, B. 1, 1, 1. W, 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 W. V, V, V. A.
With this, I think if you heard it through my laptop, it was pretty close to real time, which was quite incredible because, as I said, I'd saved those weights. And because of that, any time you signed, it would take about like 34 milliseconds to recognize the sign. And it would just wait until your hand was relatively stationary in order to be like, hey, this is a sign, I should detect it. I then also moved on to time series classification, which was used for the dynamic gestures. There I only used 4 specific gestures, so common ones such as hello, thank you, goodbye, I love you, those ones. And there I did achieve a much lower classification accuracy, just because we're now dealing with time series classification. We have to segment our data using a moving window, and this is definitely one that I need to improve on and get better with over time. In terms of my final thoughts, I guess it's been a bit of a journey that we've been on today. I guess I'm really just grateful to have had the opportunity to share this with you. In terms of what I would do next or differently, probably would have built the components myself, specifically the flex sensors. They're quite easy to build yourself, probably great side hustle if you were to sell them as well. But other things that I would do is just work on the dynamic gestures a bit more, also work on capturing emotions using visual-based methods. But I think for this to be truly assistive, we need to start looking at all of those 5 parameters I showed you in the beginning, and not just what your hands are doing. I also love to play video games, so I've actually been adapting the gloves to be like video game controllers. I started playing Hogwarts Legacy recently, and I just really want to hold a wand and do things. So that's kind of going to be the next application of the gloves. So if DevConf invites me back, we'll try that out next. But just some final thoughts. I think it's really important that you acknowledge that if you want to build this, you probably can. And as I said, I'll be sharing a recipe card on how to build this, should you choose to. I think it's also really important to iterate on this process, it can only get better, hopefully it can't get worse. Lastly, assistive tech is really, really important. I think with South African Sign Language potentially being a 12th official language, I think it's time that we really start investing resources and time and money into the technology used to build and distribute it. And lastly, my key takeaway is if you should choose to do this, definitely don't get your mom to sew your gloves. Otherwise, it'll probably cause a generational rift in your family for years to come. Thank you so much.